Hi everyone. We are going to look at a new type of function today, and this type of function is called a cubic function. So you'll notice that the equation of a cubic function will always have an x to the third power in it, so a number cubed, not to be confused with cube root. And so what we're going to do first is we're going to look at some key features of this type of function. So what I would like you to do is in your graphing calculator, go ahead and create a graph page and put in x to the third power. And let's take a look at what this graph looks like. So once you have your graph pulled up, why don't we pull up a table, so Control T, and let's take a look at some of the nice points that we see here. So we definitely have a point at 0, 0, because remember, if I take 0 and I raise it to the third power, I get 0. We should have a nice point at 1, 1, because 1 to the third power is 1. And then there should be a nice point at 2, 8, because 2 to the third power is 8. Now if I look at some negative values here, -1 would be, when I raise that to the third power, -1. And -2 to the third power would be -8. So it looks like those are the only points that I'm going to be able to fit on this graph if I'm not looking at any decimals here. And so go ahead and draw in that curve. It's a little funny to draw, but it looks something like that. And let's go through some questions here. So is this a function? Yes. We can say it passes the vertical line test. We can say every input has exactly one output. Whatever your favorite explanation is. Okay, if we talk about the domain, so the furthest left and the furthest right my graph goes, this is going to go from -infinity to +infinity. So, if I do 3 to the third power, I'm at 27, and so on. So that graph is going to continue to go left to right until infinity and -infinity. The range, so what's the lowest and what's the highest my graph goes, again, is -infinity to +infinity. X-intercepts. So it looks like there is one x-intercept, one place where this graph crosses the x-axis, and that's at 0, 0. Y-intercept, same thing, one of them, 0, 0. Where is the graph increasing? Okay, so remember we read our graphs from left to right. And so if I take my finger and I follow my graph from left to right, we are always increasing. So it's increasing everywhere from -infinity to +infinity, which means it's never decreasing. So if I trace that function with my finger, my function is never going down. Okay, it's always going up. So where is it decreasing? We would say never. Where is f of x negative? Okay, so remember, this is really asking you, where is y negative? So where are my points that have a negative y coordinate? And again, looking left to right, anywhere from -infinity to 0, I have values that are negative. Okay, so I'm looking at my interval in terms of x. Okay, so when x is -infinity all the way to when x is 0, all of my points are going to have a negative y coordinate. Now let's talk about that point 0 though. Remember, 0 is not considered to be positive or negative. So when I write my interval from -infinity to 0, I want to make sure I don't include 0. Okay, so anything up to 0 but not including it is considered to be a negative y value. So where is f of x positive, or where is y positive? So going back to the graph here, y is going to be positive anytime x is between 0 and infinity. I'm always going to have a positive number when I take those numbers and raise them to the third power. Again, we don't include 0 because 0 is not considered positive. So it's anything after 0 all the way to infinity. Okay, where is f of x equal to 0? So basically, where is y equal to 0? Well, on your graph, y is equal to 0 when x is 0. So we're going to say when x is 0. Okay, find f of x when x is 11. So this is saying find y when x is 11. Well, looking at the graph, we don't have that point. We don't have the point 11 comma something. So what we're going to do for this instead is we're going to use our equation that they gave us. So instead of f of x equals x to the third, I'm going to say f of 11 equals 11 to the third. So if we type that in our calculator, 11 times 11 times 11, or 11 to the third power, we're going to get 1,331. So that's the value of y, or f of x, when x is 11. Okay, for what x values is f of x equal to negative 512? Okay, so they are asking us to figure out, again, given that y is negative 512, what is x? So my recommendation would be to look at your table that you have pulled up on your calculator and look for where you see y being negative 512. We're looking for what x value is that. Okay, so if you scroll into the negatives, you should see that when x is negative 8, y is negative 512. Okay, it would never be a positive number here because any positive number to the third power will always give me another positive number back. Okay, so if you are looking at a negative, it's because your original number that you raised to the third power was negative. Okay, the maximum value of the graph. So what's the highest our graph goes? Infinity. And the lowest our graph goes, the minimum, is negative infinity. And then our last questions here, as x approaches positive infinity, f of x, or y, approaches what? So as we go to the right on our graph, what happens to our y values? They increase, so they also go to infinity. But as x goes to negative infinity, so as I go left on my graph, what happens to my y values? They also go to negative infinity. Okay, so those are some key features of the cubic function. So now what we're going to do is we're going to look at some other things with cubic functions, okay? So one thing that we talk about with cubic functions are the roots. And you guys have heard the word roots when we did quadratic functions. Remember, the roots were the same as the X-intercepts, or where the graph crossed the x-axis. Cubic functions have roots also, okay? So it's where does that function cross the x-axis? So I'm going to show you how to find the roots algebraically, which means without a graph. But before we do that, I'm going to remind you how to find the roots of a quadratic function algebraically. Okay, so it says solve the quadratic equation. So this brings us way back to earlier in the year when we learned about how to solve a quadratic equation using either factoring or completing the square or the quadratic formula. So I am going to try to solve this quadratic equation by factoring. Okay, so what I'm going to do is, in order to do that, I have to get everything to one side so that my equation equals 0. So I'm going to start by adding 12. So x squared plus 7x plus 12 equals 0. So now what I do is, if I'm using my factoring method, I think, okay, what multiplies to be 12 and adds to be 7? And the two numbers that work are 4 and 3. So that means I have x plus 4 and x plus 3 equals 0. And then to solve this, if you remember, we split this into two different equations, x plus 4 equals 0 and x plus 3 equals 0, which means my answer for this one is -4, because to solve for x, I would subtract 4 from both sides. And this one, I would subtract 3 from both sides to get -3. Okay, so my solution to that quadratic equation is -4 or -3. Okay, so now it says graph the quadratic function and state the roots. So notice that the thing we just dealt with was an equation. The next thing we're going to deal with is a function. And the only difference is that the function has y equals, where the equation has 0 equals. Okay, but they really are the same thing. It's just how we label them, or what we call them. So go ahead and get a new graph page opened. And I want you to type in that graph, x squared plus 7x plus 12. And so what I'm going to show you is how we find the roots on our graphing calculator, which we've done before, but let's go over that quickly. So once you have your calculator all set and you can see your graph, you might have to adjust your window. The way that we find the roots is we go into Menu, Analyze Graph, and then we go to zeros. So the zeros are the same thing as the roots in this case. Okay, so once you hit that button, it's going to say lower bound, upper bound. Remember, lower bound means place your cursor to the left of the point you're trying to find. So pick one of the roots to start with. And when you have lower bound on your screen, you're going to make sure that cursor is a little bit to the left of that point. And then when it says, and then you press enter. And then when it says upper bound, you move your cursor so it's a little bit to the right of that point and press enter. And if you did it correctly, you're going to see that that point pops up, and it should say that it's -4, 0. Okay, so that is the first one. Now, the other one, you should be doing the same thing. Menu, Analyze Graph, zeros, lower bound, little to the left, enter, upper bound, little to the right, enter, and you should see that the other thing that pops up is -3, 0. Okay, so we're basically getting the same exact answers that we got if we were to solve it algebraically. Okay, so it says describe the relationship between the solutions to the quadratic equation and the roots of the quadratic function. So the relationship is that they're the same. Okay, so the solutions to the equation are always the same as the roots. Okay, so now what we're going to do is we're going to learn how this applies to cubic functions. So if we look at a cubic function, again, the way that you can tell it's a cubic function is that it has an x cubed in it. Okay, and so we have never dealt with solving cubic functions before. This is the first time that you're going to see this. But believe it or not, it's done very similarly to a quadratic equation. The difference is that we don't do completing the square and we don't do quadratic formula. Okay, so our only choice right now is to solve this by factoring. So if you look at your equation, it's already set equal to 0. That's perfect. So what you want to do now is you want to start by taking out a GCF, okay, because I can see that there is a GCF here of 2x. So if I take out a 2x and then I divide the whole equation by 2x to see what's left, I'm left with x squared plus 5x plus 4. And then don't forget to bring down your equals 0. Now, inside the parentheses, I see that I can factor this again because it's a trinomial. So what multiplies to be 4 and adds to be 5? 4, and 1. So we would have 2x, that was our GCF, and then we're going to have x plus 4 and x plus 1. Okay, and then just like we did above where we split this equation, now I have 3 parts that I'm going to solve. The first part is 2x equals 0. The middle part is x plus 4 equals 0. And the last part is x plus 1 equals 0. So to solve each of these, the first one I divide by 2. I get x equals 0. The second one I subtract 4. And I get x equals negative 4. In the third one I subtract 1. And I get x equals negative 1. So those 3 numbers are the roots of this cubic function, or the answers to this cubic equation. So let's see if we can get those same roots by graphing. Okay, so go ahead and open up a new graph, and we're going to type in the equation just as we see it here. So 2x to the third plus 10x squared plus 8x. Okay, and you should be able to see it in the window, standard window. And let's go ahead and do the same thing that we did before. So we're going to go and find our zeros. So we're going to Menu, Analyze Graph, Zeros, and we're going to do the lower bound and the upper bound for each of the points that we see there. Okay, so this might be a good time to pause the video. Make sure that you get those same 3 roots, and then you can replay it. All right, so after you've graphed, you should have gotten those same 4 roots on your graph. Okay, so this would have been 0, 0, this would have been negative 4, 0, and negative 1, 0. So those were all your x-intercepts. Okay, so describe the relationship between the solutions to the cubic equation and the roots of the cubic function. Well, they're the same. Okay, so the solutions to the equation are always the same as the roots. Okay, so not a coincidence, it's just that's another way to solve these equations, okay, algebraically versus graphically. Okay, next thing. Believe it or not, cubic functions have a turning point, just like quadratic functions, just like absolute value functions. Okay, so that turning point can be found, just like those other functions I just mentioned, by picking out the h and the k from our equation. Okay, so this should be old news to you now that this is the 3rd time through finding turning points from an equation. So remember, when you take out the h, it becomes the opposite sign, and then the k stays whatever it is. So looking at example 1, I can see, okay, here's my h. There's a plus 0 out here that wasn't written. That's my k. So the turning point for this cubic function would be negative 1, 0, because I take out that 1 that was in the parentheses and it becomes the opposite sign. Since it was x minus that number, x minus negative 1 was positive 1. Okay, number 2, again, there's a plus 0 on the end. So the turning point here would be positive 3, 0. Number 3, what's missing here is our h. So if I had rewritten this in this form, this is what it would have looked like. They just didn't need the plus 0, so they didn't write it. So here, our turning point would have been 0, negative 5. Okay. Next one's a little bit more obvious because it has both the h and the k. So this would turn into 2, 7 as our turning point. Number 5 is missing the k, which means it must have been 0. So this is 4, 0. And number 6 is actually missing both the h and the k. So let me show you how this would have been written. Okay, so it would have looked like that. So because there's nothing in the parentheses with that cubed, we know it was 0. and there's nothing added on or subtracted at the end, so it's also 0. Okay, so that's how you can find the turning point of a cubic function. All right, so the last thing we're going to talk about with cubic functions is the relative maximum and minimum versus the absolute maximum and minimum. Okay, so we talked a little bit about this when we first talked about key features of functions, and I explained to you that the absolute minimum and maximum mean what is the absolute highest or lowest your graph goes, where the relative maximum minimum you can think about almost as turning points. So I think with cubic functions this will be very clear because they always take on the same shape, and so you'll be able to see where those relative max and mins end up. Okay, so looking at this first function in red here, let's do the absolute first. So the absolute maximum, the highest your function will go, will be infinity, because that arrow just shows that it's going to keep going up forever. The absolute minimum is going to be negative infinity, because again, the arrow shows that it's going to go down, and that just goes on forever. Okay, so the relative max and relative min are kind of the new things here. So when you're thinking about relative maximum and minimums, I want you to think of turning points, okay? So here and here are two turning points of your graph. So the relative maximum is that turning point that's higher, and we write the point of that. So the point there is -2, 1. Our relative minimum is our lower turning point, which in this case is 0, -3. Okay, and it will always work like that for cubic functions, where those relative max and mins are your turning points. Okay, last question about that graph. Over what interval is the function increasing? Okay, so if I take my finger and I trace that function from left to right, I'm going to say, okay, it's increasing, then it's decreasing, and then it's increasing again. So the interval where it's increasing is actually two separate intervals. So let's talk about the first part. The first interval that it's increasing over, remember we talk about the x's when we talk about increasing, is from when x is -infinity all the way until x is -2. That's when it stops increasing. Okay, and I'm using parentheses because it's never increasing at a certain point, it's only between the points. Okay, and I'm going to show that I'm connecting these two intervals together. And let's see, I'm going to start back up increasing when x is 0, and I'm going to increase all the way until x is infinity. Okay? All right, let's take a look at two more graphs here. So here we're just looking for relative max and relative min, because it seems as though our absolute max and min will always be the same, right? Infinity for max, -infinity for absolute min. So it's the relatives that are going to change. So if you look at your turning points, here's 1, here's 2. Your relative maximum is going to be 1, 5. Because that's the higher of the 2 points. And your relative minimum is going to be 3, 1, because that's the lower of the 2 points. Okay, another one here, so we'll just assume there's arrows here. Sometimes when I create these graphs, I can't get the arrows on the end. So for the relative maximum, we're looking at this point right here, which has a coordinate point of 0, -1. And the relative minimum is this point right here, which has coordinates of -2, -5. There we go. All right. These last two questions, I'm going to have you practice finding using your graphing calculator. So go ahead and open up a new graph page, and I want you guys to type in that equation, -2x³ plus 7x squared minus 3x. You shouldn't need to adjust your window to see your relative max and relative min. So what we're going to do is when we are finding specific points like this, we're going to use the maximum and minimum keys on your calculator. Okay, so once you have your graph up, we're going to go into Menu, Analyze Graph, Maximum. And what we're going to be asked to do, again, is to find the lower bound and upper bound. So we're going to put our cursor a little to the left of our relative maximum point, and then a little to the right for upper bound. And then when we press Enter, we're going to have the coordinates of that relative maximum. And we're going to round them to the nearest hundredth because they are not very nice decimals. Okay, so if you did this correctly, you should be getting that your relative maximum to the nearest hundredth is 2.09 and 6.05. Okay, now we're going to repeat that process for the relative minimum. So go ahead and press Menu, Analyze Graph, but now Minimum, and we're going to do lower bound, upper bound around that relative minimum point. And again, we're going to round those values to the nearest hundredth. So if you did it correctly, you should be getting 0.24 and negative 0.34. Okay, so what I'd like you to do now is pause the video, go ahead and try number 4, and when you think you have both your relative max and mins, you can come back, press play, and we'll see if you got them right. All right, guys, so if you found your correct relative max and mins for these are the answers you should have gotten. And actually, I didn't follow my own rule of rounding to the nearest hundredth. I'm going to take that back. I'm going to say 2.33. That's to the nearest hundredth.